Hello, Brainly Academy families. Today we are discussing about Kirchhoff's rules. In this video, we are going through certain basic principles and a way to understand actually rather than rehearsing Kirchhoff's rule. Because most of the time students just try to rehearse Kirchhoff's rule, but that's not correct because in the meanwhile you may really forget about that. So we are going those concepts that most students are struggling through, and if you have been in trouble with this law, just follow this video up to the end, and don't forget to smash the subscribe button and like button if you like this video. Let's go into the video. So Kirchhoff's rule. So you see, Kirchhoff's rule is nothing, or Kirchhoff rules in Italian, and then in English it's called Kirchhoff, but it's okay if you say Kirchhoff. Kirchhoff. Kirchhoff is a German scientist. He's a German physicist actually. He's a German physicist for the first time who have done this principle. So it's named after the owner of German physicist Kirchhoff, or Kirchhoff in English. So this law is nothing strange, but it's a rule or a principle those we use to solve complex circuits. As you remember, we have discussed about the series and parallel combination of resistors and bodies and any other circuits in circuit components. And this parallel and series combination of circuits can be either added or its resultant resistance and the current flowing through each and every circuit can be calculated by using simple and very easy ways. But as this circuit become very complex, it is very difficult to find the resultant or the equivalent resistance and the current flowing through each and every component of the circuit. So that times we use Kirchhoff's rule or Kirchhoff's rule. So what are the two laws or principles that Kirchhoff's rules use? These are two principles that you have to remember every time you are using Kirchhoff's rules: the junction rules and the loop rules. As you know, loop means something which is closed, which is loop, and junction means a point where some two things join. And it must substitutionally. You can assume it as a road that's moving and divide at certain point. And this point is called junctions. You will understand why it is called junction rule here. For example, if 20 people have been traveling on this road, and if some of them passed through or took this pass, some of them and took this pass, but you see, if 20 people are there here, if 10 people follow this pass, 10 people must follow this pass. And on junction rule, it states, loop rules, it states, if there is 20 people on this loop, if 20 people started moving or circulating this path, 20 people must go back as far as no circuit leakage is there. That's what it tells us. Let's dive in it. Why Kirchhoff's rule? As I said earlier, some circuits are too complex to reduce to a single equivalent resistor. That's why we use Kirchhoff's rules. Kirchhoff's rules is an extension to parallel and series combination of circuit analysis. We use it to analyze and to solve a complex circuit where the circuit is very complex. Again, it is very useful to calculate unknown current and voltage. As we have discussed in earlier videos for grade 10, on parallel combination, series combination, at least voltage and resistance will be given to us. Now here in this rule, in this principle, There is no voltage that's given to us. Some voltage may not given to us. Resistance may not given to us. So we are using them and others and calculate. So it's based on the conservation laws. So conservation of charge. There are two conservation laws that use: the law of conservation of charges conservation law, which is junction rule, we call it, and the law of conservation of energy, which is the law of conservation of energy, which we mainly refer as a loop law. So let's dive. The first one, the first principle of junction. The first junction rule or current law, it's also called current law or Kirchhoff's current law or KCL. We call it KCL or current Kirchhoff's current law. Whatever current enters certain a given point, what it says, whatever current that enters a given point in a circuit must leave that point because charge cannot build up or disappear, what it says. You see, if there is a certain circuit and this circuit divide at this point, if 2 ampere has been flowing through the circuit, there must be 2 circuits as a total that enters these junctions, which means there's no current build up or there's no current loss. On another means, in another way, for example, if there are 2 parallel circuits, combination of resistors that's carrying 2 ampere here, it's also they say 4 ampere here, 4 ampere here. So if these two things are current has been flowing through the circuit, they must add up together to give us the resultant of 6 ampere at this junction. Junctions. At this point, these two currents meet each other, so they give us the leaving current. If this is I1, if this is I2, and this is I3. Let's name them for time being. I1 is the sum of I2 plus I3. Why? Because charges never build up or from nothing or never disappear, which means the current that's coming, that's passing through the circuit come from these two parallel junctions or the divided branches of this circuit. That's what the first Kirchhoff's law or the Kirchhoff's current rule tells us. Kirchhoff's current rule tells us that one. Kirchhoff's current law. So it say according to this one. So if I1 has been flowing through this one, and if it divides at certain point, it must give us so I1 must attach. And if this is I2 and this is I3, it must give us I1 at the point, this point. That's what it tells us. That is what it says. So the junction rule statements of charge conservation, which means it is another statement of charge conservation, or it is the law of parallel. If you remember, it's a parallel conservation of parallel circuit combinations. The current is divided at the point where the parallel circuit resistors will be combined or form junctions. So this point is called junction. So it's why this junction rule. It is a statement of a charge conservation. It's a statement of charge conservation. It tells us that charges will never disappear or never add up or build up. It's never build up. That's it. For example, let's assume it as a water flowing through a pipe. Let's take the analogy for it. The current entering a junction, look, I1 entering this junction is equal to the current flowing out at these two paths, I3 and I2. So I1 must be equal to I2 plus I3. That's what junction will tell us. And let's assume the analogy to this one. The net volume of water flowing through a pipe. ይሄ ፓይፕ ውስጥ የሚገባ ውሃ ከሚወጣ ውሃ ጋር እኩል, which means the V1 and V2, this V3, let's say, if 20 liters flow in here and 3 liters flow through this pipe, there must be 70 liters that's passing through this. That means the volume will never disappear. So the water that is dropped here from this pass must flow through this one and through this one. There's no, as far as there's no the way to leak out ይሄ ፓይፕ ምን እስካልሆነ ድረስ ማለት ነው እስካልተቆረጠ ድረስ that's what Kirchhoff's rules tell us. The current entering a certain junction must leave at another junctions, or it must derive through all the alternative paths through the circuit. That's what Kirchhoff's first rule tells us. Let's come to the second loop law, or loop law, or Kirchhoff's voltage law, KVL. Kirchhoff's voltage law, KVL, or loop rule, or the law of conservation of energies. This tells us the sum of all potential difference around a closed loop is zero. Let's take you back to the law of parallel conservation of charge, whatever. What does it lose? Let's say 20 volt is there. So as we know, the charge is conventional current. We are considering conventional current here in this Kirchhoff's rule. The electric field in this circuit, so because in battery, the electric field is, now here is the problem of the students. As we move charge from across this circuit, we have 20 volt of energy here. This energy provided matter, it's called battery. Battery is to provide energy for us. So as we move across this circuit, here there is a resistance. There is a pushback. There is a resistance. There is very great resistance from due to this one. So we have to push charges to pass through this resistor. So certain energy will be dropped here if you want, and certain energy will be dropped here also the same, and the like if there is many circuits in this one. So the energy will be dropped here. You see, dropped. That means it will be negative because the energy has to be lost in the form of thermal energy or something like that. Energy loss መደረግ አለበት እዚህ ጋር ማለት ነው። እዚህ ጋር energy loss ይደረጋል. And the total loss of energy, you see, the total minus V1 minus V2, the total sum of all energy dropped across each component of the circuit, which will dissipate the energy of the circuit, will be equal to the total energy 20 volts. Or it tells us that if we add initially 20 volts plus minus of V1 plus minus of V2, so the total voltage drop and voltage raise at the beginning, and voltage drop at each component which dissipate the energy of the circuit, their sum will be zero. Across the loop. What is loop? A loop is certain አንድ ነገር ማለት ነው። ለምሳሌ እቺን ነገር እዚህ ሰርኪዩት ላይ ብቻ ነው ያልኩት። I create a loop. So ተመልሼ እዚህ ጋር ሲመጣ energy conserved ይደረጋል. So I will have 20 volt or 0 if I add it with 20. ሁሉንም እዚህ ውስጥ ዲስፕሌይ ያደርጋል። የሚተርፍ ኤነርጂ የለም። They will divide this voltage across their loop. So voltage sign convention. So assigning symbol and the direction to the current in all branches of the circuit is very essential for Kirchhoff's rule. So current እና እንትኖችን ማስቀመጥ ግዴታ ነው. So for example, if we have this one, this circuit, if we do have this circuit, each circuit ቢኖረን, so I have to give voltage sign. So the voltage sign at each resistor will have certain sign, and the current sign has a certain sign. So we shall not worry about guessing the direction of the current incorrectly, but at the end we will take the negative sign because of the opposite, if it is opposite direction. So for example, if I assume the current flow this direction or that direction, it doesn't matter, but at the end, if it is correct direction, I will obtain positive current, and if I took it in the wrong way or wrong direction, I will take negative, so which indicates the opposite of the conventional current. But the magnitude will be the same. That's the sense. Current can't be negative, so whether you got negative or positive at the end, you can take it. Magnitude will be the same. It only indicates, the negative only indicates you are assuming, or the initial guess of the direction will be It was opposite. So steps to solve circuits in Kirchhoff's by using Kirchhoff rules in order to solve certain problems or problems in a Kirchhoff. By using Kirchhoff's rule, you have to choose the direction of traversing the loop and the consistent going through either constantly going through either direct clockwise or counterclockwise. So let's go and see one by one how to choose a direction. Now look here. Here is a point where most of the students miss. I want you all to focus here. I want you everyone to focus here. Now look, as we move conventional current, if this is positive terminal and this is negative terminal, conventional current always flow across the circuit. And the resistance is this direction. The resistance is this direction. Because the resistor won't resist the charges to not flow through them. So certain energy must be needed. ይሄ ማለት ምን ማለት ነው? አንድ ነገር ለምሳሌ assume you are pushing this up አንድ ነገር ወደ ላይ እያነሳችሁ ነው እንበል። ወደ ላይ ስናነሳ በራሱ አይሄድም። ምክንያቱም ኢነርጂ ይፈልጋል። ይሄ ማለት እኛ ኢነርጂያችን እያወጣን ነው ማለት ነው። Which means you have to exert certain energy in order to move this charge against this resistance because the resistors resist the current to not flow through that. To not flow through it. So, if the resistor, the current is in the direction of, if you choose the direction of current in the direction of conventional current, for example, if you choose this one as your current direction, and the conventional current direction is also the same. The conventional current direction is also the same. Thus, you see, the conventional current direction is that direction. If you choose the direction of your current that way, the voltage will be dropped because you need much energy to move that charge across that resistor from positive terminal to negative terminal. Thus, the voltage drop will be negative if it is across the conventional current. But if it is in opposite direction, which means if you are moving against a conventional current because it's electron that's needed now, you don't need any more any potential energy. So the electron must drop their energies. Raise their energies, have positive energies added to move that charge across that field. So across a field, we need so we need energies, external energies. That's why. So if we are moving across, against the conventional current, you have a positive potential energy, positive endothermic. That's we need. Again, across a battery, if you are passing as you're moving, as you're creating the loop, if you are passing through this thing, I want to remind you this negative terminal, this positive terminal. The electric field is this direction now. You see, electric field is this direction. So current is created due to the electrons. Electrons are negative charge, even if we are considering conventional current here. As we are moving from negative terminal to positive terminal, we assume it has to be positive. Why? Because we are moving against electric field. You see, so from so as we are moving from negative terminal to positive terminal, which means from this terminal to this terminal, we are moving against electric field. If we are moving against electric field, we assume it to be positive because we need this external energy to be spent on the charge to move it against the electric field. And if we are moving again across from positive terminal, that's direction, from positive terminal to negative terminal, we are moving across electric field. You can assume like you are moving in a waterfall. ውሃ ወደ ታች እየፈሰሰ ነው ብላችሁ ወሰዱ። ይሄ ውሃ ወደ ታች የሚፈስ ውሃ ላይ ብትተኙ ወስዷችሁ ይሄዳል። ምንም ሌላው ተጨማሪ ኤነርጂ አያስፈልጋቸው because ውሃ ወደ ታች እየፈሰሰ ስለሆነ። But if you are moving against the waterfall, you need much energy or you may fall even. So you can assume like that. እንደዛ assume ማድረግ እንችላለን። generally ምንድን ነው ያወራነው? So in resistor ውስጥ the electric field is always from in the conventional current direction positive to negative ነው flow የሚያደርገው conventional current positive to negative and the electric field is that direction. And if you are moving across it, you don't need any energy across in the direction of conventional current kahona, because conventional current always flow from positive terminal to negative terminal, and this is electric field is that direction. And if you are moving across electric field, you don't need any external force, so you have to lose this energy, so it's negative, there's no voltage, so voltage drop. If you are moving against the electric field, you need external energy, so it's positive. If you are moving against electric field, again, because electric field in the battery is this direction from positive terminal to negative terminal, so as you're crossing this one, you have to spend certain energy, so that's positive. You have to get external energy from the battery, and if you are moving again across it, it will be negative. Why? Because energy must be dropped. That's all. Okay, now let's solve this problem by using the concepts that we have discussed so far. Feel free to pause the video and to try it by yourself first. Okay, so the question says find the current I1, I2, and I3 from this figure. So to solve this problem, we have to use Kirchhoff's rule, because we cannot use this series and parallel circuit analysis directly, because it is two circuits which are joined together, and so it's a little bit complex to use it. And again, we can use another methods like Norton and Thevenin's circuit analysis, but Kirchhoff's law is very effective for this problem. Let's do this. All right, so according to Kirchhoff's first law, let's use Kirchhoff's current law. It says the current that is entering certain junction must leave that junction equally. That means the current entering certain junction must be equal. We have around 6 junctions. Now we can use one of these junctions. We can use either D, A, B, C, E, or F if you want. For time being, I like to use this junction. So this is C junctions. As you see, the current entering the junctions are I1 and I2. So I1 plus I2 are entering the junctions, and the current is leaving that junction is only one current. So it means the I1 and I2 add up together to give us I3, as we have discussed so far, as we have seen here. See, the thing is flowing in is equal to the amount of substance flow out based on the flow rate. So similarly, let's do this one. This is a first Kirchhoff. From Kirchhoff's first law, we do have this one. Now let's go to the Kirchhoff's second law, which is Kirchhoff's voltage law or loop law. Now we have to create two loops, which we can use for this problems. We can create any loops that we want. So we can create two loops for this circuit separately. ለዚህ circuit ለብቻ we can create a loop. Let's create this loop this way, and let's rotate this that way, and let's check this one also the same direction. We can put up actually the opposite direction, it doesn't matter. Just the matter is the way we put the sign for each component as we move through a circuit. Now let's consider this loop 1 and this one as a loop 2. For loop 1, let's start from this one. So at this point, the electric field is this direction, because this is positive terminal to the negative terminal. So to move this charge across this circuit according to our loop, so as we are going through this circuit, we are moving against electric field. So for that reason, we need endothermic process, which will give us an energy. That means an energy from certain point must be raised, which is 10 volt.
which means if we are moving against the electric field across certain device, whatever device, it can be battery, it can be a resistor or capacitor, whatever. If we are moving against the electric field, the potential will rise, so we'll take positive point here. And let's move to this one. Here the potential electric field is from here, it's negative, it's positive, it's negative, so electric field is that direction, and we are moving along the electric potentials. You can take it as like a waterfall. If water is falling downward, and if you place something here, you don't need any energy to move that object. Unlike it will, rather it will lose its own energy because it does not need energy to be support it. But if you're moving against this waterfall, it needs a positive energy. So as we are moving across this electric field, this charge is moving across this field because the current, conventional current indicated it. We use negative of 6 I1 volt must be ohm, because as we know, the voltage at drop at this point is how much? It is the current that's passed through I1 times the resistance. And let's proceed. This then, let's go all the way to this one. I3 come here, and I3 pass through this one. So conventional current is still is in this direction. So the electric field is this direction, and the direction that we, of our loop also indicates the same way. So it's also moving across electric field. Electric field is that direction because it's positive terminal, this negative terminal. So if the current is the way, the path that we have chosen by our loop is in the direction of the current flowing, we think the voltage will be dropped at that point. The voltage will be dropped. So it will be negative, how much? Twice of I3 ohm, which must be 0, which means the voltage rise at each point and the voltage drop at each point must be added together to give us 0, because energy is conserved, not created, not dropped. The amount of energy raised must be dropped across each resistor in the circuits. That's what it tells us. So 10 volts minus 6 I1 or plus, minus 2 I3 is equal to 0. So from this one, we think minus 6 I1 minus 2 I3 is going to give us minus 10 volt, 10 ampere, because they cancel each other. So when we take this one, 6 I1, let's simplify by minus 2, let's simplify this thing by minus 2, and again this is by minus 2, also this one by minus 2, minus 2. Then finally we'll obtain this thing, 3 I1 plus I3 will give us 5 ampere. This is the second equation that we have to cut an addition to that one. Let's proceed. Let's rewrite what we have got here. I1 plus I2 will give us I3 according to Kirchhoff's first law, and 3I1 plus I3 will give us 5 ampere. This is from the Kirchhoff's second law of using this below ones. Now let's use the upper loop and find the certain equation that will help us to do that. All right, so from this loop, let's move. On this battery, we are moving along a battery. along the electric field of the battery. So the energy will be dropped here because we are moving along the battery, as I said. If we move from positive terminal to negative terminal, the electric field in the among the batteries terminal is from positive terminal to negative terminal. If we are moving according to our loop directions, this direction movement we are dropping our energy because of we don't need energies at that point. So it must drop this amount of volts. So it will be negative. This amount is minus 10 volts. And we are moving this direction, so the current is I2 that passes through this 4 ampere for almost electric current I2 because there's no other current that must pass through this 4R. So it's moving that direction, and sorry, this is a positive terminal, this is negative terminal, so electric field at that direction, so we are moving along the electric field, so it will be dropped minus 4I2 minus 4I2, and similarly we move all the way to this direction, and when we reach this one we are again moving along the electric field along the electric field in that direction, and we are moving along the electric field. If we choose this path, we are moving along the electric field, so we'll take it as minus 14 volt again. Again we move all the way to this way, and now here this is a positive terminal, and this is a negative terminal because a conventional current is this direction, so this must be positive terminal, this is negative terminal. So we are moving against the electric field, you see, against the electric field. So we need a positive energy to move this charge across that, if we assume the path to be that direction. So which is going to be plus 6I1, which is equal to 0. So let's add similar one, minus 10 volts, minus 14 volts, which is going to be minus 24 volts, minus 24 volts, minus 4I2, plus 6I1 is equal to 0. So let's simplify by 2, I think, minus 2 by minus 2, which is going to be by 2 minus 4I2 first. Let's shift that one to that direction. I1 is equal to 24 ampere. Then let's divide by 2 by 2 by 2. Then it's going to be minus 2I2 plus 3I3 I1 is equal to 12. Now I've got 3 equations, you see. We've got 3 equations, and we can substitute one into another and solve it for I1, I2, and I3. Let's do that. Alright, so now we have got the third equation, which is, let's still simplify it. Actually speaking, now this is in terms of I2 and I1, and this is in terms of I3 and I1, but I can substitute for I3 this one. So let's substitute and solve for that in terms of I2 and I1. So 3I1 plus I3 means I1 plus I2. I1 plus I2. So I substitute this one to this one, is equal to I2 is equal to 5 ampere, which means 4I1 plus I2 is going to be 4I1 plus I2 is going to be 5 ampere. So we've got 3 similar equations. So we can rewrite this one. We can rewrite this one as like this one. So I don't need this one also. Okay, so this is 4I1 plus I2 going to be 5 ampere. And let's simplify this one, or solve this one simultaneous by using simultaneous equations. We can use simultaneous equations of solving 2 linear equations that has 2 variables. So 4I1 plus I2 is going to be 5, and this is 3I1 plus 2I2 minus so I2 is going to be 12. Let's multiply this one by 2, which is going to be the upper one by 2 sinabaza. What is going to be is 8. It's going to be 8, and it's going to be 8. Actually speaking, it's going to be 8. This is going to be minus, plus twice of I2, and that's going to be 10 is equal to 10 when we multiply by 2 in order to make it simple. Now here, let's add them together. Let's add them together. I don't need this one also, since I already get it. So let's add them together. So now when we add them together, 8 plus 3 is 11 I1s. This will cancel each other. So 10 plus 12 is 22. So I1 is going to be 22 divided by 11, which is equal to 2 ampere. So we've got I1. So I1 here is gotten to be 2 ampere. Now let's substitute I2 and find I2. 4 times I1, which is equal to from this one, we can find for I1, I2. 4 times 2 ampere plus I2 is going to be 5 ampere. So I2 is going to be 5 ampere minus 8 ampere, which is equal to minus 3 ampere. It's minus, which means we have moved in the direction opposite to I2. So we chose the wrong direction, but it doesn't matter that its magnitude is the same. So we'll take I2 as to be 3 ampere, that's minus 3 ampere. Why? Because it's already, because current has no direction, it only indicates the wrong way that we have chosen when we are choosing the loop. It doesn't matter. So I2 is going to be 3 ampere in magnitude, but we will take it as a negative. So I3 is the sum of the two currents, because it's the sum of the two currents. Alright, so let's say solve for I3. I3 is equal to I1 plus I2. Let's solve for that. So which is going to be 2 ampere plus, which is 3 ampere minus 3 ampere. Because of the direction, we have to add them rightwise now. Likewise, them rightwise. So 2 ampere minus 3 ampere, which is going to be minus 1 ampere. It's going to be minus 1 ampere. But again, finally, after getting the answer, when we get a right answer, we write it. But in our calculation, we have to consider the negative sign because it indicates the path that we have chosen. But at on the final answer, we'll put it positive, right? Because we don't need to write we need to write the final answer is positive because current is not a vector, and we use the negative sign just to indicate the amount of current is the path that we have used is in opposite direction. So let's write I1. I1 is 2 ampere, I2 is just 3 ampere, and I3 is just 1 ampere. So that's it. But just, you see, it's all about it. Thank you very much.